We've already looked at unordered priority queues where the items aren't kept in any particular order. Now let's consider what happens if we actually require that they be in a particular order. So we'll look at ordered priority queues. So our ordered priority queue implementation will rely on an ordered collection of data. So the items will be in order based on their priority. But that begs the question, are they in ascending order or descending order? So our implementation will use an array to keep track of our items. In fact, we'll even use a fixed size array. So our insert operation's job is to find the proper place to insert something and insert it. So at the end of the insert operation, all of the items in the array should still be in order by priority. Extract min should remove and return the highest priority item. But let's revisit this idea of whether we want to use ascending order or descending order. So take a minute and try and come up with a compelling argument for why one may be better or worse than the other. Okay, I'm going to argue that descending may make the removal process slightly easier because we won't necessarily have to relocate all of the items that follow the item we're removing. I say may because there are workarounds to this that would make ascending order work pretty well as well. It's just usually the most intuitive, straightforward approach is easier if they are in descending order with the highest priority item at the end of the array or furthest to the right in the array. Peak min will return the highest priority item, but it won't remove it as always, and is empty will return true if the array is empty if we have no items left in our priority queue. So let's repeat the example that we've already done with the unordered priority queue, and this time we'll go through it using our ordered priority queue with an array. So just like before, we'll start out by creating an instance of our ordered array-based priority queue. In this case, we're passing in a value that represents the maximum size of the priority queue. So our priority queue will never have more than 7 items in it. Then we'll go through our operations. So the first thing we'll do is we'll insert our 247. The next thing we'll do is insert 1. And remember that I've decided to keep the highest priority item furthest to the right. So my values will be in descending order by priority. So I'll have to start at the beginning of my array, and I'll have to find the proper inserts point for the item I'm trying to insert, the 1. So in this case, 1 definitely comes after 247. I've got an available spot, so I'll go ahead and put the 1 in there. Let's do another insert. So in this case, I'm going to insert 131. So again, I'll start at the beginning. 131 comes after 247. Again, we're going in descending order, but it comes before 1. So I'm going to have to start here and shift everything over to create a space, and then insert the 131. Repeating the process, we'll insert a 200. We'll start at the beginning, identify that 200 comes after 247, get to 131, 200 comes before 131. We'll go ahead and shift everything after the 131 over, and we'll insert 200. And we'll move on to our next operation. So our next operation is an extract min. Now, the real advantage of keeping the minimum item at the back of the array is that we just simply remove it and we don't have to shift everything over if we had left a gap. Our next operation is a peak min. Again, we just look at the last item that's stored in our array, our 131, and we'll return that value. So just to back up for a second, our extracted and removed 1, our peak is going to peek and see the 131. Next, we'll insert -5. So again, we'll start at the beginning. We'll see that -5 is after 247. Again, we're sorting in descending order. It's after 200, it's after 131, and I've hit a free space. So I'll go ahead and put the -5 in. Next, we'll do an extract min. Well, again, we just start at the last available item in our priority queue, and we extract and return it. So we'll remove and return the -5. Now we'll insert 100. Same process as before. We start at the beginning. 100 is less than 247. It comes after 247. It's less than 200, less than 131. We've hit an available spot, so we'll go ahead and put it in. And we're done. Our next operation is peak min, and again our minimum value is already readily available at the end of the array, so we will return but not remove our 100. Okay, let's review our ordered array approach. So our insert may require that we iterate through finding the location to insert something, and then once we've found that spot we may have to shuffle things after it over. So it will pretty much always go through all n items in the array. The first segment it'll go through to find the insertion point, then after the insertion point it'll go through shuffling everything over one position. So this leads to an interesting question. Under what conditions would all the inserts be constant time? Can you think of something that would cause all of the inserts to take constant time? Okay, let's review the extract. So extracting something is always taking something from the end of our array, the last position that was filled in. So we could do that in constant time. We need to somehow keep track of where that last position is. Peak min is, of course, just looking at that last item but not actually removing it, so it can also be done in constant time. And is empty is also able to be done in constant time.